Last time we have seen that there is a decomposition of the Riemann curvature tensor of a Riemannian manifold, and this is a result of an entirely algebraic consideration. So we recall that if we have a Euclidean vector space, a finite dimensional Euclidean vector space, then we have looked at a certain space of 0,4 tensors, namely we take one the space of skew-symmetric 2 tensors, and then the space of symmetric tensors of those. So these are 0,4 tensors, which are skew first pair, skew the second pair, and then we can interchange the two pairs without sign. And then there was this decomposition. So let's say the metric here is called Q. Then there was this decomposition that was given as multiples. So we called it UV plus ZV plus WV. So that was a certain subspace of this one, and then there's a space missing, which is 1 to 4 star. So these three pieces make the space of algebraic curvature tensors. So this was singled out by the Bianchi projection. That's the image of the Bianchi projection, and that's the kernel of the Bianchi projection. And this UV, or the corresponding decomposition of a curvature tensor, then looks like this. So we have split a curvature tensor R into the UV part, which is just a multiple of Q co-cardinal meso Q, and the multiple that we have is scalar curvature on 2 times n minus 1, n is the dimension of my vector space, plus then this part is related to Ricci curvature, more precisely to the traceless part of the Ricci curvature, because the trace is already here in the scalar curvature. So that is the traceless part of the Ricci curvature, n minus 2 co-cardinal meso symmetric. So that's the ZV part. And then there's the rest, which we call the Y curvature. Alright, so that's the decomposition that we have. And now let me and then you can look at special cases where one of these three components vanish, or several of them vanish. And many of these cases are special geometries or little classes of geometries of special interest. So let me make a table here. So let's say the vanishing of, let's say, if the UV part is 0, or the ZV part is 0, or the W part is set to 0. So what does that mean? So this means what? So for example, if they are all 0, so let me just pick it, plus it. So meaning that all parts are 0, so that means the full curvature tensor vanishes, and that just means that the manifold is flat. Vanishing curvature. Now, what I want to do, yes. So if only the first two parts vanish, but the third one not necessarily, so this part vanishes and this part vanishes, it means the traceless part of Ricci curvature vanishes, but its trace, the scalar curvature, also vanishes. So that just means the Ricci curvature vanishes. So that would be a Ricci flat manifold. Now you could also look at the case where only the traceless part of Ricci vanishes, and then that means that Ricci curvature coincides with the multiple of the identity. So that is the case of an Einstein metric. So that's the Einstein condition. Then we could also ask for these two parts to vanish. So what does that mean? So that means the curvature tensor is just given by this first part. And so it's just a multiple of Q coordinate with Q. And for this, you can compute, so let's do the computation, what happens to the sectional curvature. So if we just have a multiple of Q corresponding with Q, and so I want to evaluate the sectional curvature on a plane. So then, so evaluate the sectional curvature on a plane. So therefore, how do I do that? I choose an orthonormal basis of that plane and insert it in the curvature tensor, right? So of x and y of a normal basis of some tangent plane. Then I have to take that guy and insert this orthonormal basis into it twice. This gives me the sectional curvature in general for the curvature tensor. I'm ignoring this prefactor for the moment. And well, let's see what we get. So by definition, I have to apply Q to these two times the other Q to the other two plus. And then I have to do the same thing with the two factors interchange, but that's the same because the two factors coincide. So I actually get this once more. And then I have the negative contributions, which are given by taking the outer and the inner pair. So that would be Q of x, y times Q of yx. And then again, interchanging the pairs gives me the same thing. So I get it twice. But since this is an orthonormal basis, so actually this guy is 0, so this does not contribute. And this one is 1, and this one is 1, 2. So the result will be 2. So that's what we have. Now if we take this one, in case that the other two terms vanish, or if I just take this part, 2 times Q, and apply this to these vectors, so form the scalar curvature of that, then so this gives me 2. This cancels the 2 here, so I get scalar curvature on n times n minus 1. And what does this tell me? Well, this tells me if these other two parts vanish, then the sectional curvature of my curvature tensor will at each point be independent of the plane. It will be given by the scalar curvature. And in fact, if you have a constant for your sectional curvature and you compute the scalar curvature out of it, you take two traces, which gives you these factors n and minus 1. So it's consistent. So this, so if we cross out these two, this implies that sectional curvature is constant at each point, right? And it's essentially it coincides with the scalar curvature. And if you restrict ourselves to the case of at least 3 dimensions, 2-dimensional case is boring anyway, because in that case R is always just given by this first tangent term. If we restrict ourselves to the dimension at least 3, then this condition that the sectional curvature is constant pointwise, so a priori it might vary from point to point, but at each point it does not depend on the choice of plane. That's what we have. But this actually implies that it also does not depend on the point, as long as the manifold is connected, of course. So that's something called a sure lemma, and that the sectional curvature is actually constant and also does not depend on the point. It's a consequence of the second Bianchi identity. So in other words, if these two terms, these two parts do not occur, then it follows that the sectional curvature is constant. Conversely, if the sectional curvature is constant, then this gives you the curvature tensor. Sectional curvature and curvature tensor carry the same amount of information. They can be computed out of each other. So if this gives you the right sectional curvature, this is the only curvature tensor that gives you the constant sectional curvature. So see that this is equivalent to constant sectional curvature. And then there's another thing that you could look at, namely that you ask for vanishing of only this W part, and then the thing is called conformally flat. So you see this decomposition into pieces is of great geometric relevance, because you have all these different kinds of geometries or geometric conditions popping up, which are studied a lot in all kinds of contexts. Okay, yeah, this is nothing that people look at. You could, in principle, so if only the traceless Ricci part vanishes and nothing else, yeah, this is nothing people study. Somehow it doesn't come up naturally. Good, but an interesting observation that you can make though at that point is that in case the dimension is equal to 3, so for n equal 3, remember for n equal 3 last time we saw that this W part is actually not there. So then we always have, of course here this means doesn't mean that the spaces are 0, it means that the corresponding component of the curvature tensor is 0. But here we have that the space is 0, so the curvature tensor is also 0. So it doesn't matter whether we have a cross here or not. And so this says in particular that these two cases are equivalent. In that case, Einstein is equivalent to constant sectional curvature. And also, these two cases are equivalent. So Ricci flat is equivalent to flat. And usually the right-hand side is stronger than the left-hand side, but not in dimension 3. Good. And that's interesting because this gives us the first examples of manifolds which cannot carry an Einstein metric. So, example, the manifold, for instance, S2 plus S1 does not admit an Einstein metric. And why is that? Well, if we had an Einstein metric, it had to be of constant sectional curvature. Otherwise, S2 plus S2 has a metric with constant sectional curvature. Call the constant, let's say, kappa. And now we have to distinguish two cases to rule them out. So I'm claiming this is not possible. So this manifold cannot have a metric of constant sectional curvature. Why not? Well, if kappa is positive, then this would mean it has positive constant sectional curvature. In particular, the Ricci curvature would be positive definite. Right, so if the sectional curvature is positive, then in particular the Ricci curvature is also positive definite. But we have a theorem of manifolds with positive Ricci curvature about saying something about the fundamental group in Riemannian geometry. So what do we know about manifolds with positive Ricci curvature? Compact manifolds. Yes, what theorem is that? It's the Bonnet-Myers theorem. Right. It says in particular, it gives us a diameter bound, and it says in particular also that the fundamental group has to be finite. But the fundamental group of this guy is of course not finite. fundamental group of S2, which is trivial, times the fundamental group of S1, which is Z. That's a contradiction. So that's not possible. And the other case is negative or zero sectional curvature. And in that case, there's another theorem. So then we have sectional curvature. It's actually not important that it's constant. We have a non-positive sectional curvature here, and there's another theorem from Riemannian geometry telling us something about such manifolds. Which is relevant in this context. It tells us something about the universal covering of the space. So this is the Cartan-Hadamard theorem. And this tells us that the universal covering of that space is given by the Riemannian exponential map at any tangent, at any point. So in particular, it says that the universal covering is diffeomorphic to Rn, R3 in this case. Universal covering of S1 across S2 diffeomorphic to R3, but it isn't, because the universal covering of this space is what? What's the universal covering of this space? Exactly, this one is already simply connected, and this one has R, and so this is not diffeomorphic to S2 plus R, so that's also wrong. It's not possible. So we see that, so we have actually shown that this manifold does not have metrics with certain sectional curvature conditions, but by this curious fact, this is equivalent that it cannot have, or this even implies that it cannot have an Einstein metric. Good. All right. Now we want to study four-dimensional manifolds, because there we have a refinement and things become very interesting, but still manageable enough to draw interesting conclusions similar to the ones that I just showed you. For the next paragraph. All right. So let's see. So let's take a look again at these algebraic considerations. Now we want to look at the case that n is equal to 4. So far nothing changes here. We have this situation in dimension 4, 2. But in addition, I want to give this vector space an orientation. And this orientation, together with the special case n equals 4, gives us a refinement. So now the dimension of V is equal to 4, and V is oriented. So then, of course, this will be applied to the tangent space of the manifold later, and so it will be a 4 manifold, an oriented 4 manifold. Good. And this orientation gives us something interesting, namely, the orientation implies that there's an operator on forms, which is called the Hodge-Star operator. So Hodge-Star operator in general. So this is induced by the orientation. So in general, it goes from K forms to n minus K forms. Here in this, so to n minus K forms. But I'm looking at the case n equals 4. So I have 4 minus K forms in our case. And I restrict my attention to the case K equals 2. Then I have 4 minus 2. And that's 2 again. And that's the important thing, that this space goes from lambda 2 to lambda 2, and you could have this in higher dimensions too, in even dimensions, where you would have the Hodge-star operator acting on middle degree forms. But it's important to have 2 forms, because we want to apply it to this decomposition where 2 forms form up. This is why what I'm saying today works only for 4 manifolds as an orientation. And this operator is characterized by the following. So if you take a form and you want to apply the star operator to it, then the scalar product with some other true form gives us a number, and this is given by, so this number is given by, well, you could just take the wedge product of the two forms, which would give us a 4th form. And now the space of 4 forms in 4 dimensions is 1-dimensional, so this is spanned by the volume form. And so this guy has to be a multiple of the volume form, and that's supposed to be the multiple. So volume form is just E1 star, which E2 star, which E3 star, which E4 star, where E1 up to E4 is a positively oriented orthonormal basis of V. And the stars mean I take a dual basis. 1 up to E4 star, a dual basis of V star. And this is why the orientation plays a role, so that because it does not depend on the choice of the positively oriented orthonormal basis, but if you switch orientation, then you get a sign. Alright, so and this characterizes completely this Hodge-star operator, because if you know the scalar product of star omega with any other vector here, then you know the vector. Good. And so what properties does this Hodge-star operator have in these dimensions and degrees? So dimension 4 and degree 2. So first of all, star is always a self-dual operator. Symmetric operator. And in this case, in these degrees and dimensions, the square of the Hodge operator is equal to 1. It can also, in other degrees and dimensions, it can also be equal to -1. It depends on the parities of k and n. But in this case, which is of interest to us, it's equal to 1. And now we have an operator, star, acting on this vector space lambda 2 V star, which is self-dual and squares to 1. Since it's self-dual, it's diagonalizable, so it has eigenspaces, so V star decomposes into eigenspaces. But since the the square of the operator is 1, the eigenvalues can only be plus and minus 1. So we can decompose this space into the +1 and -1 eigenspace. Therefore, lambda 2 V star decomposes into the +1 eigenspace, which I call lambda plus of V star, and the -1 eigenspace. Like this, where lambda plus or minus of V star is the set of plus or eigenspaces, so that means the set of all omegas in lambda 2 such that star omega is equal to plus or minus respectively. Alright, and also we know that since the operator is self-dual, this sum here is perpendicular. And in fact, these two sums also have equal dimension, which one can see by writing down, by using this basis here and deriving from this a basis for lambda plus and lambda minus. So what is the dimension of lambda plus V star then? So for this we have to know what is the dimension of lambda 2 V star. It's 4 on 2. It's 4 choose 2, which is 6. And so these two spaces are 3-dimensional. And in fact, you can easily write down a basis for these two spaces. So coming from this basis, this oriented basis of V itself. So then, well, we can take a look at this wedge product. So what would happen if I apply the star? Of course, this star has nothing to do with that star. Yeah? So let's just do a basis, and this is the Hodge star operator. So if I apply the Hodge star operator to this one, what would I get? You can directly read it off from this characterization. So what would that be? Exactly. E3 at G4. So if you want to have something in the lambda plus space, just take the sum of these two, right? And then we have something which maps to itself under the star operator. And we can play the same game. We can take E3 wedge E1 wedge E3. So what would I get if I applied the Hodge star operator to this one? And why is it a minus? Exactly, if you wedge these two guys here, then you get E1, E3, E2, E4. In order to get the volume form, you have to do one. This is the minus sign. And then we also have E2 wedge, I would say, E1 wedge E4, which gives us E2 wedge E3. And this is again with a plus. And so these three guys are obviously independent, and they provide a basis for lambda plus. And the basis for lambda minus is easily obtained by just flipping the signs here. And you get the basis for lambda minus. So these are these three-dimensional bases of these. Right. Good. Now, why am I interested in this? Well, let's look at this again. Here we have this space lambda 2 V star popping up. And now, in the four-dimensional oriented case, I can split this. So let me do that. So I can also write this as lambda plus V star plus lambda minus V star. And then take symmetric bilinear form on this one. So now, how does this look if I start from this? Well, so you have a vector space which is split into two subspaces, and you are interested in symmetric bilinear forms on that space. And if you write this with respect to bases, if you write this as matrix, this means that a representing matrix of such an element would be given by a 2x2 block form, right? A symmetric matrix, which is a 2x2 block corresponding to this splitting. And if it's symmetric, then in particular, we have something symmetric in this block. So the upper block, so the upper and left block corresponds to lambda plus, let's say. So here we have some symmetric block sitting here, which then describes exactly the symmetric bilinear form on lambda plus. So I can get symmetric bilinear form on lambda plus. Similarly, we have a block down here, which gives me a symmetric bilinear form on lambda minus. And finally, we have these off-diagonal blocks. And we have two of them, but they are essentially the same because of the symmetry of the whole matrix. This is just the transpose of that. But this one is then arbitrary. And this then corresponds, this matrix then describes a metric on lambda plus on in one argument and lambda minus in the other argument, which is are independent. So this gives us simply the space lambda plus V star tensor lambda minus V star. So this this decomposition. Alright, and looks a bit different from this decomposition we have up there, and which is strange because this is an ON, a decomposition into O4 in this case, 4 dimensions, 4 modules, meaning that the group O4 acts on this space, and these spaces are invariant subspaces, and I told you actually that these are irreducible subspaces. So this is and if you have a compact group acting on a finite dimensional vector space, this got decomposition into irreducibles, it's unique. So we have these 4 parts, and here we have only 3 parts. Oh, that's strange. And in fact, this decomposition is no longer an O4 decomposition, because this decomposition is only invariant for the subgroup SO4, because it has to preserve orientations. So that is this is a decomposition into SO4 modules. And now everything that is O4 equivariant is of course also SO4 equivariant, because that's a smaller group than this one. But here we have only 3 spaces, and we should at least get 4, maybe even more, because it might happen that one of these spaces, which is irreducible for O4, decomposes on the SO4, which is a smaller group. That could happen, right? But so far we have less actually. So which splittings am I missing here? Somehow, something must be split further, right? So these pieces cannot all be irreducible. And there's one way to split something further, which is completely obvious. So this can always be split in the multiples of identity or metric plus the trace field part. So let's do that. So then here we get, so if I identify by linear forms with endomorphisms using the metric, then I can write this as last time as the identity of lambda plus. Yeah. What did I call it? Lambda plus V star, everything that's generated from this, plus the trace-free things left in here. And similarly here, so now I have R times the identity on lambda minus, plus the trace-free things left in here. Plus this one. Okay, so we have this splitting actually, but now we have 5, right? So here we have 4, and now we have 5. And so let's see how these things are actually related. And so one thing that we see is here we have a one-dimensional space, and here we have a one-dimensional space. Here this is a one-dimensional space, and there's another one-dimensional space. This one. Right, lambda 4 in 4 dimensions is also one-dimensional. So let's perhaps write down the dimensions to see what can possibly relate. So here we have dimension 1, here we have dimension 1, here we have dimension 1, and here we have dimension 1. Alright, now what else? So, what's the dimension of this one? Trace-free, symmetric, bilinear forms in 4 dimensions. You just have to count entries in a matrix. So the things are described by 4x4 matrices, which are symmetric and traceless. 9, that sounds good. Because without the traceless condition, it would be 4 plus 3 plus 2 plus 1, which is 10, minus 1 is 9. So this one is 9-dimensional. And now the question is, what's the actual dimension of this part, of this while part? Well, we have derived a dimension formula for the space of algebraic curvature tensors. And the general formula, let's remember, n minus 1, n squared, n plus 1, divided by, what was it? 12. Yes, it was 12. So in case n is equal to 4, then this is 3 times 4 cancels the 12. So we are left with another 4 times 5, so it's 20. Yeah? So this one here is 20 dimensional. So that means there are 10 dimensions left for the while part. So that's what we have. Aha, okay, good. Now let's see. For these spaces down here, so that's traceless, symmetric on a 3-dimensional space. What's the dimension? That's 5. And that's also 5. And what's the dimension of this one? This is something that you don't have to think about. This must be, the answer must come spontaneously. 3 times 3 is 9. Okay, aha, that's interesting. So we see the 9 popping up here and there, and the 1 is popping up twice here and there, and then we have a 10 here and 2 5s left here. And then we see how things relate, but we can also make it more explicit. So one might think, or one might ask, now concerning these two one-dimensional spaces, which one corresponds to which one up there? And what would you think, this guy? To which one would it correspond? The last one? No, it's not true. But it also doesn't correspond to the first one either. Namely, let's see. So if you look at the identity here, the generator here and the generator here, and we add them, then this gives us the identity on the whole space, right? And that is the generator of this one. And similarly, if you take the difference, then, well, what is that? It's the identity on lambda plus and minus the identity on lambda minus. So that's exactly the Hodge-Star operator. This was the plus 1 eigenspace, and that's the minus 1 eigenspace. So this is the Hodge-Star operator. And this then corresponds to a generator. So if you take this and the corresponding bilinear form to it, you will see it's totally antisymmetric. And so it's not true that this space corresponds to one of these spaces or that one, but the sum of the two correspond to each other. They are sort of linked. Yeah? Okay. Anyway, now since these decompositions are unique, we must have that this guy coincides with that guy, simply by dimensional reasons. So, okay, so uv plus lambda 4 v star is equal to r d lambda plus v star plus t minus, and zv is equal to this part. You can also check this explicitly by taking any element in here and applying to two vectors, one from, let's say, 2 from lambda plus, and you will get 0. 2 from lambda minus, you will get 0. And the last one is this one. And this is then given by these two, sum of these two 5-dimensional spaces. And I give those two spaces a name, namely, I call them W plus V and W minus V. So what's actually happening here is we have this decomposition as O4 modules, but if we restrict these O4 modules to SO4 modules, to this somewhat smaller group, then this space is no longer irreducible, but rather decomposes into these two subspaces. So we have a finer decomposition. So that's what's happening. And we will make use of that. Good. And now we have to relate this somehow to our characteristic classes. So let's see how that goes. So maybe we should. We recall the formula or composition formula for the curvature tensor in this four-dimensional case. So now we are in 4 dimensions, so our splitting is now scalar curvature divided by 2 times n minus 1 is 2 times 12 is 24 plus the traceless Ricci part divided by n minus 2 is 2 plus, and now the wild curvature just decomposes into these 2 pieces. So that's the decomposition that we have now in 4 dimensions and oriented. Good. And our characteristic classes are computed out of curvature matrices. And somehow this decomposition must be related in these curvature matrices. So remember that if I look at the curvature matrix with respect to a local orthonormal frame, then the definition was given as, well, take the curvature tensor, apply these vectors, and then we get an homomorphism of the tension space, and we insert the vector j here, and then expand the result in the basis that is given to us. But in the case of an orthonormal basis, the prefactors occurring in the expansion are just given by the scalar products with the corresponding vectors. So we have this formula. Right? So again, this basis E1 to E4 is orthonormal. It's a pointwise computation that I'm doing here. And by definition, this was, when I want to consider the curvature as a 0,4 tensor, this was x, y. Now I have to interchange here because of this minus sign convention. So I get an EI and an EJ. So that's what I have. And this is the curvature tensor that I have up here. So that's here you see this is a 3-1 tensor, this is a 4-0 tensor. I use the same symbol because I assume you always know which one you mean by context. And now we can use this decomposition, and this gives us a corresponding decomposition of the curvature matrix. And it should be interesting to know what we get if we take these expressions that are of interest to us in the curvature matrix, like the Pfaffian for the Gauss-Bonnet theorem, and see and express things in these terms. So let's remember the Pfaffian of a matrix, of a 4x4 matrix, look like this, right? A, B, C, D, E, F, and here we have minus A, minus B, minus C, minus D, minus E, minus F. And the formula of the Pfaffian was A times, in the 4-dimensional case was AF minus BE plus C. So that's the formula for the Pfaffian. If I remember correctly. And then this means if I insert a curvature matrix instead, so what do I get? Well, I get the 1-2 entry here, and multiplication is the wedge product. So I get 1-2, and this, and F is the 3-4 entry, minus minus, then I have the 1, 3 entry, which, and C is, sorry, that's not right, it's an E. This times that. That's the 2, 4 entry, plus, and then I have C and D, so which gives me 1, 4, which omega 2, 3. Right, so that's the problem. And the Gauss-Bonnet theorem tells me, up to a certain factor involving phi, if I integrate this guy over the manifold, then I get the Euler number. And now, let's see, in order to get this, to get a hold of this integrand in the Gauss-Bonnet theorem, what we actually only have to do is, this is a 4 form. It's a 4 form, so it lies in a one-dimensional space. So this is always just a scalar multiple of the volume form. And that's the integrand we are interested in, this multiple. So really what we are interested in is this guy, when evaluated on my vectors E1, E2, E3, E4 from the local frame, because that's exactly the prefactor that I get in front of the volume form. Okay, and well, then what you have to do is you have to compute these things. And for example, if we apply this to the first term, this means I have to take the wedge product evaluated on these 4 vectors. So what will this give me? This gives me 1, 2 evaluated on E1, E2 times 3, 4 evaluated on 3, 4. And then I have to take 1, 3, and this comes with a minus sign, so first 1, 3 times second factor on 2, 4. And the last term is 1, 4 and 2, 3. So I'm just inserting the definition of the wedge product. So which gives me first factor 1, 2 evaluated on E1 and 4 times E3, 4 evaluated on 2 and 3. So that is the first part, and then you have these 2 other parts, which I'm not writing down. Good, and for these terms, you can insert these terms now, and you see you only have these, the only things that occur are these orthonormal vectors from the basis that come in to game. And for this, then you can insert these 3 terms or 4 terms up there, and then compute the whole thing. I would not recommend to do it by hand, and I'm not going to do it here because this would take up the rest of the hour of the lecture today. But it can actually be delegated to a computer algebra system if you want. And anyway, so if you just carry this out after a long and tedious computation, you end up with the following expression, namely a very nice and simple expression, 1/2, and then what we get is the norm of the first term of the decomposition involving scalar curvature squared minus the second one squared and plus the W part. So here I'm not doing any splitting. Yeah, that's what we get. So I could also write this as W plus squared plus W minus squared. So that's the result. In fact, there is also another approach to get to this formula, not involving so much computation, and if I have the time at the end of the lecture, I will sketch that. Right, so this is a translation of our Pfaffian applied to the curvature form into these parts of the curvature tensor that actually, in the end, give rise to the curvature. All right, so what does this tell us? Of course, this gives us a more explicit form of the Gauss-Bonnet theorem in 4 dimensions. So remember, the Gauss-Bonnet formulas told us that if the Euler number of our manifold is given as the integral of the Pfaffian of the curvature matrix on 2 pi. And so we have this 2 pi factor, so that Pfaffian in 4 dimension is quadratic. It's quadratic in the entry, so I can pull this out. And I get a 1 on 4 pi square. Integrate it over. And then I have another factor of 2 here, which actually gives me an 8 here. And then this is the integrand. Integrated ordinary. So in dimension 2 we have a very simple formula of a very simple form of the Gauss-Bonnet theorem, because then we just integrate the Gauss curvature, which is essentially the scalar curvature. Here it's more complicated, but still manageable. And as an interesting corollary, which was first observed by Bishop and Goldberg, 1964, we find the following, so that M be an orientable, for this we don't, not actually, so that does not orientable compact 4 manifold. And then, and it's interesting to look at this integrand, because we have squares here, it's all squares, but they come with different signs. And so we may wonder, okay, what happens if this one guy with the negative sign is simply not there? Then we have a positive integrand. And this vanishing of this guy, we discussed this in the beginning of the lecture, is equivalent to saying that that is an Einstein manifold. So it's a 4-dimensional Einstein manifold. Then the Euler number of a manifold cannot be negative, because we have an integral, which is the integrand is this square plus that square. So certainly it cannot be negative. And also we can say something about the equality case, namely the Euler number vanishes if and only if, well, in order to vanish, the whole integrand must be identically 0. So that means the scalar part must also vanish, and the W part must also vanish. So the whole curvature tensor must vanish. That means that M is flat. So that's a statement about 4-dimensional Einstein manifolds. And now let's see if we can find examples, if we can use this somehow. In the beginning of the lecture, I showed you an example of a 3-manifold, which does not allow an Einstein metric. So this corollary should be help us to find a 4-manifold which does not allow Einstein metrics. Well, the only thing we have to do is to find a 4-manifold with negative Euler number. Should be doable. So how can we do that? Well, we need this lemma on the Euler number, namely the Euler number. So if M and N are compact manifolds, then the Euler number of the product is the product of the Euler numbers. Maybe that helps. Let me postpone the proof for a few minutes, and let's see if we can now cook up 4 manifolds which have negative Euler number. Well, if I want to cook up a 4-manifold as a product manifold, then I will probably have to take 2 surfaces. Because if one of the factors is one-dimensional, it has to be the sphere that has Euler number 0, and then this is not going to work. And so as an example, we might use two surfaces. So let's denote by FG compact connected oriented surface of genus G. Then the Euler number of this guy is well known to us. What is it? Yes, 2 minus 2G. And so what we can take as our manifold is, so one with a positive and one with a negative factor. So let's take S2 cross FG. The Euler number of this one, so it will be the product of the two, and the Euler number of S2 is 2. The Euler number of this factor is this one, so we get 4 times 1 minus G, and we see that this is less than 0 if G is at least 2. Therefore, this manifold for G at least 2, it cannot carry an Einstein metric. Okay, so no Einstein metric on this manifold if G is at least 2. Well, how about the case that G is equal to 1? Let me say something there too. Let's see. If G is equal to 1, then the Euler number is actually exactly 0, right? And the Euler number of this product, so the surface of genus 1 is the 2 torus. So maybe I write 2 torus here. F1 is a 2 torus. Now this is 0, and we can say something about the equality case here, right? If this carried an Einstein metric, it would have to be flat. Therefore, S2 cross T2 is flat. But that's not possible. Why? So S2 cross T2 can certainly not carry a flat metric. And we have the argument already today. Well, that's not so clear. It doesn't have to be a product metric, right? I'm not saying that it has to be a product metric. It could be some weird flat metric such that if you restrict to its S2 factor, it's not flat. Yeah, the Cartan-Hadamard theorem, right? The Cartan-Hadamard theorem tells us that if the manifold is flat, or more generally, the eccentric curvature is non-positive, then the universal covering of the space has to be diffeomorphic to R4. But it's diffeomorphic to S2 cross R2. Same argument that we used in the case S2 cross S1. Exactly the same argument. So that's not possible. So we see it's also not possible to have an Einstein metric if the genus is equal to 1. How about genus equal to 0? If the genus is 0, then the surface is S2. So does S2 cross S2 carry an Einstein metric? Yes, it does. The standard metric is, of course, Einstein, because the standard metric of S2 has, each factor has Ricci curvature 1, and then the product is also Ricci. Yes. So for G equals 0, it does have Einstein metric, a very simple one. All right, good. So that's a consequence of this observation here, and this non-existence of Einstein metrics on certain manifolds that we have seen in dimension 3 and 4 is remarkable insofar as it's an open question to date whether such a thing can also happen in higher dimensions. So does every compact manifold of dimension at least 5 carry an Einstein metric? there are no obstructions like this corollary that we've seen, but also there's no general existence statement. And the general belief amongst the experts seems to be that actually the answer should be yes. So that in higher dimensions it's not obstructed. But it's open. Good, so that's the Gauss-Bonnet theorem in dimension 4. And let's also take a look at the signature theorem, Hirzebruch signature theorem in dimension 4. Let's see if we can make that explicit too. Of course we can. I should also prove the lemma maybe, for the sake of completeness. Proof of lemma. Or did we do it already? I don't think so. So the Euler number of a manifold can be written down in various ways. One is to look at the cohomology and take the alternating sum of the dimensions of the cohomology. So I could write this as the alternating sum of the so-called Betti numbers. So that's a general statement. Where Betti numbers are the dimensions of the corresponding homologies. The M is compact, these homologies are finite dimensional, so it makes sense to define these Betti numbers. That's the Euler number. And well, how about a product? Well, for the product, so we have the Kühlet formula for the cohomology, right? So the homology of a product is given as the direct sum of tensor products of cohomologies L of the first factor, tensor H I minus L of the second factor, where you sum from L equals 0 to I. That's the Kühlet formula. So if we now take dimensions, this tells us that the ith number of the product is equal to the sum, and this is the dimension of the tensor product is the product of the dimensions, so this is the L of m times the I minus L of n, I equals 0 to L. And now we have to take the alternating sum of that, right? So we have to take minus I to the L, minus I to the minus 1 to the I, sorry, minus 1 to the I, and then sum over I. So that's sorry, sum over L. Yeah, this is from L equals 0 to I, yes. And so then I can keep that. And I have to sum over I here. That's the number of that. And this guy is easily seen to be just the alternating sum. N is the dimension here of the product manifold. So maybe I should write M1 plus M2 for the dimensions of these two. Then that's 1 plus M2. And here, of course, then the individual things go only to N1 for M. Group together the terms that add up to the same, where I and J add up to the same L, and then you resum that. So this gives us no dilemma. All right, so that's the Euler number, and since we are at it, before coming to the signature, let me state another theorem, another lemma about the Euler number, namely the lemma. What happens if I take the connected sum of two manifolds? What happens to the Euler number in that case? So let even dimension, of equal and even dimension of m and the same, so that I can form the direct sum, and it should be even. Why should it be even? If I take odd-dimensional manifolds, what happens to the Euler number in the odd-dimensional case? 0 anyway, so that's not interesting. So in the even-dimensional case, if I look at the connected sum, I have to be oriented also. The connected sum, and I take the Euler number of that, and it turns out that's the Euler number of the m plus the Euler number of n minus 2. And why is that? Proof. So here I use the characterization that I can triangulate my manifolds and count simplices of various dimensions, take the alternating sum. So let's say this is the manifold M, this is the manifold M. Let's take triangulations of the manifold. And still over here, I draw only one simplex here. And now I form the connected sum. So what do I actually do in the connected sum? I remove two balls, open balls, small open balls from the manifold. So then I get manifolds with boundary. The boundary is a sphere. And I glue in that sphere across an interval. So I form this bridge between the two manifolds. I glue in interval cross sphere. And the identification has to be made in such a way that the orientations match. This is why I have to talk, I'm talking about oriented manifolds here in order to perform the connected sum. But now let's look at the Euler number. Well, removing a ball is essentially, an open ball is essentially removing an n simplex here and here too. That means removing a ball. So that means that if I do the counting of simplices in these calculations, then I have certainly all the simplices from n and all the simplices from n, but I have removed an open ball here and an n simplex here too. Now n is even, so this is an even dimensional simplex that I'm removing, and that enters with a positive sign in the Euler number. So actually n ball here removed, n ball here removed, that means minus 2. But that's not the only thing that I'm doing, because then I'm also gluing. And when I do the gluing, this just basically means I identify all the boundary simplices from the ball that I've removed here with the corresponding ones here. They get identified. But that means that all concerning all these simplices here, the number is reduced. So the number is just only half of them left. So what was 2 n minus 1 simplices, for example, this one here and that one here, is now only 1 because they get identified. So what I'm doing is, if you do the count, I'm removing also all the simplices that are coming from the boundary here, but only once. Right? The open thing is removed twice, but the boundary parts are removed only once. And now, what contribution does this give me? I mean, this is these n minus 1 simplices that are removed once, but also the lower ones, right? Like the vertices in this picture. And they have to be counted with the correct sign also. Right? So, well, what's the topology of the boundary of a ball? It's a sphere. And so I'm talking about the triangulation of a sphere. And that is removed once, so really what I'm removing is the Euler number of the sphere. And so we don't have to do any counting. And the good thing is, this is an odd-dimensional sphere, so in fact, this is 0. So this gives me this formula. Now you may wonder, what happens in, just for the fun of it, let's look at the case that is odd-dimensional manifolds. I could do the same argument also in odd dimensions, right? And but we know in odd dimensions that all these Euler numbers are 0. But now what happens here? I mean, I'm removing this ball, so I'm removing something. And this Euler number here, then this is an even dimensional sphere. that actually has Euler number 2. So I'm subtracting another 2 here. So what's wrong? Yes, that comes with a plus 2 because at the end simplex enters with a negative sign in that case. So we have plus 2, minus 2, and it cancels out, so that we actually have the sum, but they are all 0 anyway. So everything's okay. Everything's fine. Good. So we have that. All right, and now let's turn to Hirzebruch's signature theorem and rewrite that in 4 dimensions. And this requires, so what was the integrand in the Hirzebruch signature theorem? This was this L class. That was a class derived from the Pontryagin classes. And so we really have to understand the Pontryagin class in 4 dimensions better first. And well, okay, maybe in order to apply this, this gives us the possibility, in fact, to get more examples of negative Euler number in 4 dimensions. For example, you could now look at the case 4 torus sine 4 torus. If you look at that Euler number, that gives you the Euler number of the 4 torus plus the Euler number of 4 torus again, 2 times minus 2. That's what you get from this formula. But the 4, what's the Euler number of the torus? 0, yeah, it has a flat metric. So the Riemannian metric, and so the Pfaffin is 0, but Gauss-Bonnet-Chern is 0, so we don't have to do any counting here. But in fact, so that's 0, so we get minus 2, it's also negative, and therefore this manifold by the Goldberg-Bishop observation has no Einstein metric. So that's an example which is not of product form like the other examples that I showed you earlier. So it's easy to come up with examples that way. All right. Now, but finally, the Pontryagin class. So following along, and this in fact holds in all dimensions, and it also holds for all vector bundles, not just a tangent bundle. So let E over M, or let F be a real vector bundle over a manifold M, and let omega be the curvature matrix of connection on this bundle with respect to some local frame. And then I can make a first Pontryagin class explicit. And in 4 dimensions, this will be the only thing that interests us because it's only in rank 4. So there are no higher Pontryagin classes in 4 dimensions anyway. So for the 4 manifolds, the first Pontryagin class is what we understand. And what I'm claiming is that this is represented by the differential form coming from taking the curvature matrix, square it, take its trace, normalize by 8 pi squared, the corresponding homology class, and the negative of it. This is seen in page 4 of the manifold. So that's a Pontryagin class. Just to make it explicit. So for the Euler number, we had to take the Pfaffin of omega, and here we have the trace of omega squared. Also quadratic, of course, in omega, because we get something in dimension 4. And why is that? Cool. So, okay, so we have to recall how we actually defined Cauchy eigenclasses. So what did we do? We took this real vector bundle, passed to its complexification, and then we took the Chern class of that, and then this was essentially the Cauchy eigenclass, up to sign. Yeah. So let's do that. So the first Cauchy eigenclass of this bundle, by definition, this is the second Chern class of the complexification of the bundle. So, I don't call it yet, sorry. And but with a minus sign. So there was this additional sign flip that we introduced. So it's minus the second Chern class. Now let's represent the Chern class by curvature. Now that's the curvature matrix of a connection on E, but we can extend any connection by complex linearity to its complexification. And then if we compute the curvature matrix of the complexification with respect to the same frame that we can still use, then the curvature matrix does not change. And the curvature tensor does not change, and the curvature matrix does not change either. So this omega is also a curvature matrix with respect to a frame for the complexification. And this is good because we basically have this explicit formula for the Chern class in terms of the curvature matrix. Namely, we had to take the determinant of 1, the identity matrix. In this case, it's identity matrix plus omega on 2 pi I. So that gives me the full Chern class. I only want the second part, so let me write 2 here. I'm only interested in the degree for the part which is quadratic. So that's what we have. And now, how can we relate it to this? Well, there's another thing that we need, namely, to recall, namely the odd Chern classes, something odd here, they vanish if I apply it to the complexification of the bundle. Right? So that's also something we should recall here. The first Chern class of this bundle, that's actually 0. This is why we did not define any Cauchy eigenclasses from them, because they were 0 anyway. And now if you look at this expression, determinant of 1 plus omega, then remember essentially, so these various degree parts came from taking the polynomial, which on the eigenvalues, if it's a diagonal matrix, let's say, which on the eigenvalues is given by the, in this case, second Hilbert symmetric function. So this would be the lambda I times lambda j summing over I less than j. However, that's not what we have here. If you replace omega by a diagonal matrix, then this trace here is the sum of the squares of the eigenvalues. Something different actually. And so we may wonder why that should be true. That's actually not the formula we expect. But let's see. If we look at sigma 1 lambda squared minus sigma 2 elementary symmetric functions, then what is it? It's this one is lambda 1 all the way up to lambda n squared minus 2 here, minus 2 times some lambda I and j I less than j. And now if you multiply this out, you get the square terms. And you get the mixed terms which are cancelled. Right? And that shows me, and now this is exactly what we have here. So that's the trace of the matrix square. So this shows me that the trace of any matrix squared is the same thing as this one, sigma 1, which is actually the trace itself, squared minus 2 times the sigma 2 thing. I call this the C2 of A. But that's C1 of A squared. And if I apply this to the curvature matrix here and take the cohomology class, we know that this contribution vanishes. So that is actually 0 in our case. So if I replace this by omega, then this one up to a factor, right? This vanishes. This is 0 because C1 is 0. And this one, C2, is up to sign, is my Pontryagin class, so this is, okay, I need also to insert this factor 2 pi I. 2 pi I, doesn't change that. This is 0, of course, omega on 2 pi I. And now that is, so that gives me the Chern class, right? So that gives me the Chern class. If I take this form and pass to the cohomology class. So that means that the cohomology class P1 of F times 2, and then there's this factor 2 pi I. I take it out, it's quadratic, so I get a 1 on 4 pi squared. But that gives me also, this I squared, gives me a sign here. And yes. So I have 3 signs in here. The I, if I pull it out, gives an I squared, which is a minus 1. Then I have this sign here, and I have also this sign here. So, and moreover, I have this factor of 2 here, which I have to divide. Actually, 1/2, because I solved for this one. So that 1/2 goes here, this gives me 1/2. And then I'm left with trace of omega on trace on omega to pi on the right side. This minus 1. So which is the formula? Okay. So it was a bit confusing the way I presented it, but I think it's clear. So we have this, that's a nice and simple expression. That's something we can work with. Let me just conclude the argument why this is interesting. Namely, now we play the same game that we played earlier with the Paphian. Since we have this explicit expression here for the Pontryagin class, so that means if I take a look at this form that represents my Pontryagin class, let's say, let me ignore the factor we can make later, and the minus sign. So that is really the sum. So the trace of a matrix squared. So let's first square the matrix. Then we have to multiply this mid. So this gives me the matrix multiplication, and then I take the trace. So that's sum I j. And by skew symmetry, if I take this for an orthonormal frame metric, which I do in the case of a Riemannian metric, then now let's pass to a Riemannian metric, and let's write down the curvature matrix with respect to an orthonormal frame. Then these matrices are skew symmetric, like for the Paphian, where it had also be skew symmetric. I can also write this as omega I, which that, and also we see by skew symmetry, it's also enough to consider the case that I is less than j. Because if I is then bigger than j, if you interchange i's and j, you get the same thing. So I can also write this as -2 times this sum, just to reduce the number of expressions to be computed. And now the same game can be played. We have these wedge products of curvature entries, and we insert. So when we insert so let's say trace omega squared, and we want to compute what we get if we insert this orthonormal frame, because this gives the coefficient of the volume form in the integral. So we have to do this with these sums as earlier, and then insert the decomposition of the curvature tensor and compute it all, simplify it, and see what remains. And in fact, in this case, it turns out the scalar curvature and the Ricci curvature contributions cancel completely. Only the Y curvature part survives, and what we find is -2 times W plus squared minus W minus squared. So that's what we get. Okay, so now Hirzebruch signature formula simplifies, namely signature of the manifold. Yeah, it's given by this L class, not by the Pontryagin class. But how is the L class and the Pontryagin class related? For this we have to know the multiplicative sequence for this L polynomial, which we have computed. And the first part that pops up, we are only talking about the P1 part, is actually just multiplication by 1/3. If you look up the lecture notes that you have made, then you will also watch again the recording, then you see that the L class in dimension 4 is just 1/3 of the L class. So that was the Hirzebruch signature theorem. That's Hirzebruch in dimension 4. And so we can write this now in this case as, so we have a 2 and a 8 pi squared and then another third here, so which gives me the 12 altogether. So 2 by 8 is 1/4, divided by 3 is 12. 1 and 12 pi squared equal over the manifold of this expression. So that's even nicer than the Gauss-Bonnet-Chern. In fact, it's not surprising that the scalar and the Ricci part do not contribute. Why? If there was also a scalar squared term or a Ricci 0 squared term, well, what happens if you interchange the orientation, if you flip the orientation of the manifold? If you do that, then the signature gets a sign. And these two terms get interchanged. So we get a sign here too. But the scalar and the Ricci part would not change. So if they entered quadratically with some coefficient, this cannot be, because it will also have to change signs, but it doesn't. And then the only way it can arise is that it does not appear in the formula. And similarly for Ricci 0. So it's if you think about it, it's not surprising. In the case of the Euler number, it was different, because if you change the orientation for the Euler number, it doesn't change. So it doesn't matter. Good. So that's for today, and we will apply this on Monday and refine the corollary of Bishop and Goldberg. And thank you for your attention.